Hi all, welcome in these 5 lectures. Today we will talk about iterative algorithm, and as we will see, it is an interesting alternative to convex optimization. Before we start the lectures, as usual, I will do a short recap of what we have seen so far. So we have seen in the second lecture that model selection is statistically interesting in the sense that it enjoys some minimax optimality, but at the same time we have seen that this is not something that we can implement in practice, at least in high dimension, because of the computational cost. So the idea of this course and what we have seen in the last lectures is to try to go from model selection to something that you can compute. And one way to do this was to do some convex relaxation of the model selection criterion. And we have seen in the last lecture that convex relaxation enjoys some nice properties. It is near minimax optimal. It is tractable numerically, so we can compute it in practice. And the only issue is that there are some bias that we have to handle in a way or another. What we will do to see today is an alternative to convex relaxation, which are iterative algorithms, which will enjoy these two properties without having this bias. So it is probably interesting. Let's have a look at this. Iterative algorithms are probably as old as computer science, essentially because they are computationally very efficient. So it was very efficient to use them on the early computer. There has been a renewed interest on iterative algorithm in the recent years, exactly for the same reason, because it is computationally very efficient. So when you work with a lot of data in high dimension, it is very efficient. And also because compared to convex relaxation, there is no shrinkage bias, which is also a nice feature. So here we will focus on some specific iterative algorithm. There are of course many different iterative algorithms, but we focus on a specific class, which is interesting for two reasons. First, because the analysis is quite simple, also I think very instructive. And as always, we will start by describing this iterative algorithm in our canonical coordinate sparse linear regression setting. So let's proceed to this. So as always, we will consider a regression which is coordinate sparse, which means that only a few coordinates of beta star are non-zero, and we will be in a Gaussian regression, so the noise term will follow a Gaussian distribution with covariance sigma 2 identity. So before introducing the iterative algorithm, I think that it will be useful to do a refresher on lasso and the proximal optimization for the lasso. So I remind you that model selection estimator corresponds to this estimator where we want to solve this optimization problem that we are not able to solve because this term behaves in a very non-convex and non-continuous way. So the idea of convex relaxation is to relax this L0 pseudonorm by L1 norm, and this gives us the lasso estimator. So this is the estimator, the lasso estimator, but as we have seen, this is something that we cannot directly compute in practice, in the sense that there is no closed form solution for this minimization problem. So we have to do this minimization numerically. There are many different algorithms for convex optimization. I have been emphasizing one of them, which is the proximal optimization algorithm that I will recall now. So what is the proximal recipe? The idea is that here we have a function that we call f of beta. So we are not able to solve this, but we replace this function by something which is easier to handle, and we will be able to compute approximate solution for this problem. More precisely, what we will do is to compute a sequence of problem. So we start from some beta 0 and then compute beta 1, beta 2, etc. By iterating some optimization where we replace this function by a proxy, which is this one. So this is a linear expansion of f around beta t, which is the current point in the optimization. And we will do optimization by replacing f by this quantity, and we will iterate, and under some condition, we will converge to the lasso estimator. So if we replace here f by this proxy, so we have this minimization problem, so this corresponds to the iteration of the proximal method, and as we have seen in the last lecture, we can rewrite this optimization problem as this optimization problem. So the minimizer will be the same for 2. And here we have something which is a simple optimization problem for which we have a closed form solution. And the closed form solution for this problem, it is given by this quantity. So we introduced the soft thresholding operator, S lambda of alpha. So what is a soft thresholding operator? So it takes as input a vector alpha in Rp, and it outputs a vector still in Rp, where it takes each coordinate of alpha, so alpha 1, alpha p, but it multiplies each coordinate by 1 minus lambda over the absolute value of the coordinate, and takes the positive part. So this is the soft thresholding operator, and what we have seen in the last lectures that this is the solution of this minimization problem, where we have 1/2 of alpha minus beta square plus lambda, the LWM norm of beta. So if we look at this minimization problem here, so alpha will be this gradient step here, so this gradient update, right? And lambda will be eta times lambda. So the solution is simply the soft thresholding operator applied at level lambda times eta, and to the vector which is obtained by a gradient step from beta t. So this is alpha, which corresponds to this step. So this is the proximal optimization method, which is based on soft thresholding. And as we have discussed, since we have a problem which is convex for eta which is small enough, this iteration will converge to the lasso estimator, which is the solution of this optimization problem. At this point, it is nice to discuss some properties of the lasso, which can be seen both from the optimization problem and also from the iterate of the proximal method. What we have discussed is that the lasso estimator tends to shrink the solution beta towards 0, and this is something that we see on the soft thresholding operator. If you look at this operator, it does two things. First, it will select coordinates which are large enough, or said in a different way, it will set to 0 coordinates which are too small. For example, if alpha 1 here in absolute value is smaller than alpha, this will be equal to 0. If alpha b is smaller than alpha in absolute value, this also will be equal to 0. So what does the proximal method? It looks at the gradient update, and it set to 0 all the values which in absolute value are smaller than eta times lambda. So this is a first effect of soft thresholding, but there is a second effect. So the first effect is to set some value to 0, and the second effect is to shrink the value. So here we do not keep alpha 1, we multiply by this shrinking factor, and this shrinking factor tends to shrink the value towards 0, right? So if you only do gradient step without applying soft thresholding, what you do is to minimize the least square, right? So you do not have bias in this case, but you do not select variable. By applying recursively the soft thresholding operator, what you are doing, you are selecting some variable because of the selection of the thresholding, but also you are shrinking the solution towards 0, right? And we can observe during the optimization process the fact that we have a shrinkage of the solution towards 0 and not the ordinary least square solution. Right, so in a sense, we have a feature that we enjoy, which is the selection of variable with the thresholding. And there is another feature we are not so happy with, which is the shrinkage of the solution. So maybe we would like to select without shrinking. And this is, as we will see, what we will do. And for this, we will come back from the initial problem, so from the solution 6.1 of the model selection criterion, something that we cannot solve, but we will try to use the proximal method on this criterion. So let's look at it. So if you want to apply the proximal method on the original problem, so what we do, we replace f of beta here by this quantity, so which is a proxy for f. And of course, we penalize now with lambda squared times the pseudo norm of beta, pseudo L0 norm of beta. Exactly in the same way as here, we can rearrange the term in order to have this quantity appearing. And the only difference is that here we will multiply by 2, right? So if we rearrange the term, we obtain this term, which is exactly the same as this one, except that we have multiplied everything by 2. And we have this term, so we do not have eta, but 2 eta, just because we have multiplied by 2. Right? So we do exactly the same computation, and similarly as here, where we have an explicit solution for this minimization problem, we have an explicit solution for this minimization problem. And this explicit solution is expressed in terms of the hard-thresholding estimator. So let me remind you what is the hard-thresholding estimator. So this is an operator which takes as input a vector in Rp, and it outputs a vector which is still in Rp, and what it does is it looks at the value. So for alpha 1, it looks at alpha 1. If alpha 1 in absolute value is larger than alpha, then alpha 1 stays unchanged. But if alpha 1 is absolute value is smaller than alpha, then alpha 1 is set to 0. And this is done for each coordinates. So hard-thresholding is setting to 0 values which are too small, so smaller than some threshold lambda in absolute value, and otherwise it does not change the vector. And as you have seen in the exercise 281, the hard-thresholding estimator, so the hard-thresholding, is solution of the minimization problem, where we look at the least square plus lambda 2, the L0 pseudonorm. So now if I come back to my problem here, what I see, so alpha is this gradient update, right? And lambda 2 is 2 lambda lambda 2. So the solution to this problem is the hard-thresholding of the gradient update, but at a level which is lambda square root of 2 eta. Right. So what we see is that if we do the proximal method on the original problem, we again have some explicit expression for the recursion, and the main difference is that the soft thresholding operator, which was appearing for computing the lasso, has been replaced by the hard-thresholding operator. Right? And the hard-thresholding operator, if we compare with soft thresholding, the main difference is, so as the soft thresholding, it will set to 0 value which are too small, smaller in absolute value than lambda, but it will not have any shrinkage, right? When alpha 1 has an absolute value larger than lambda, it will not shrink the value, while soft thresholding is shrinking the value. So this is the main difference. So if we compare to a proximal method for the lasso, we have the nice features that there is no shrinkage. So we will not have this shrinkage bias that we observe when we compute the lasso estimator. Right, but this is an algorithm, but since the initial problem, which is the model selection problem, is not convex, even if you take eta very small, we do not know what these iterations are doing if it converges to anything, right? And we are even sure that, so more precisely, if this was converging to the solution to this problem, right, then we will be able to find in polynomial time the solution of some NPR problem, something that is unlikely to be true, right? So we cannot expect that in general this iterates converges to the solution of this minimization problem, right? And even worse, we do not know if this converges to anything. We do some iteration, but maybe there is no accumulation point or limit or anything. So we have an algorithm. It will not shrink the solution, but we do not know what this is doing. And we are not even sure that it will behave as well. And the point is that here, by doing this thresholding, maybe we will lose sparsity of the solution, and maybe it will not work. It will give poor result, right? So there is an idea in order to use this nice recursion in such a way that we will be able to have some guarantee on the output of the algorithm. And the idea is the following. So first, we will fix the step in the gradient set to 1/2, so that 2 eta will be equal to 1, right? So we fix it to 1/2. We could choose something else, but 1/2 is nice. We know what we will do. And we'll start from 0. And we will apply this recursion here, but for a value of lambda that will be very large at the very beginning, so that we will be sure to have something sparse, and that will decrease to a target value, which will correspond to the min max level for optimization. So let me explain this. So what we will do, so we fix eta equal to 1/2, and we'll choose a level lambda t, which will be of this form. So it will be, for t equals 0, it will be a plus b. So a will be large, so that this will be very large. And when t will go to infinity, this will converge at a geometric rate to b, where b will correspond to the target value. So we know that the target value is something which is like sigma square root log p. So this is something that we have seen in the second lecture. So we will converge to add something like this, right? So let us write down the algorithm. So at iteration t plus 1, so at step t plus 1, we will apply the hard-thresholding at level lambda t plus 1 to a gradient update with eta equal to 1/2. Okay, so we just have 1/2. So we can write down what is the gradient of f. So I remind you that f corresponds to the least square fit. So you know by heart the gradient. You should actually. So in this case, since we have 1/2, it is equal to this thing. And we can rearrange this expression in such a way that here we have something about beta at t, and here we have x transpose 1. And in the following, this matrix here, which is identity minus x transpose x, will be defined as being capital lambda, and we see that this matrix, the properties of this matrix will be very important in the following. Right, so just I repeat again, we will use these updates here, but starting from a lambda which is very large and decreasing to the optimal value of lambda, which is something like this, which is the value that we use in model selection. Right? So the idea is to have to try to keep under control the sparsity of the solution by taking very large value of lambda and decreasing to the target value. So this is an algorithm. It makes sense. Does it work? Can we say something about this algorithm? So this is the main part of the lecture today, which is to give a Ritz bound for this algorithm. And before giving this Ritz bound, I want to discuss a little bit the nature of the analysis that we will do compared to what we have done before, especially, for example, if we compare to the lasso. So we have been looking at the lasso estimator in the fourth lecture. So the lasso estimator, remind you, this is a solution of this optimization problem, and we have analyzed the properties of this estimator, how good it is, how close it is to beta star. I emphasize that usually, since you do not have a closed form expression for this minimization problem, what you will use is not exactly this estimator, but an approximation of this quantity, which is obtained after a certain number t of iterate of, for example, proximal method. So after t iterates of this thresholding. Right, so what you use is what I call here beta t lasso, which is an approximation of the lasso. So if you want to analyze the risk, since it is really what you are using, you should analyze the risk of beta at t lasso. Right, so you should look how close it is to beta star. And there is a very standard way to do this, which is to split this error into two terms. One term which is how close beta hat lasso is from beta star. So this corresponds to the statistical error. And this is exactly what we have investigated in the last lectures. And there is the second term, which is how close beta hat t is close to beta hat lasso. So how close is the approximation from the lasso estimator. And this is a pure optimization error. So this is really analysis of convex optimization of everything. So we have not discussed this term in the last lectures, since we are most focused on statistical error rather than optimization. But you can give bound on this term, and if you want to look at the bound on the optimization algorithm, so especially on convex optimization, there are some very good lecture notes from Sébastien Bubec that you can find online, and also there are some references in the lecture notes. Right, so this is the classical approach where we split into two pieces, the statistical error and the optimization error, and we've already looked at both error independently, right? We analyze on one side the statistical error, and we analyze on the other side the optimization. Now let us consider our iterative hard-thresholding algorithm, right? So the algorithm that I have described here. If I look at the algorithm, so if I look at the iterate t, I have no idea if this will converge to anything. Maybe it will, maybe it won't. We don't know. So we cannot do this kind of split because there is no limit. Here there is a limit, we know it, we know that this will converge to this. Here there is no limit, right? So we cannot do this decomposition into statistical error on optimization. So what we will have to do is to handle both errors simultaneously. And actually, this is not both error because there is no optimization error, since we are not optimizing something. We are not trying to compute the solution of something, right? Because we do not even have convergence guarantees. So let me explain how we will proceed. The idea is that, so if we look at the estimator after t plus one step, so what we do, we look at hard-thresholding at level lambda t plus 1 of capital lambda beta at t plus x transpose 1. So this is exactly this situation. So what we will do, we rearrange this term by using the fact that capital Y is equal to x beta star plus epsilon. So if we use this expression, and we also use the fact that, so we'll have x transpose x beta star. So we will write that x transpose x beta star, it is equal to beta star plus x transpose x beta star minus beta star. So it is equal to beta star minus capital lambda beta star, where capital lambda, I remind you, is this matrix. So if we do so, what we obtain beta star minus lambda beta star. Here we have the capital lambda beta hat t plus, so x transpose epsilon, which is the last term. Right, so we look at the iterates and we separate three terms here in our iterates. The first term is beta star, and this corresponds to our target, right? So what will be nice is that beta t plus 1 converges to beta star. So of course we know that it will not be the case because we have a noisy observation. We will not be able to recover exactly beta star, but this is our target, and this is what we want to compare. We want to compare beta at t plus 1 to beta star. Then there is a statistical error. You already know the statistical error. This is the one that we have seen already when we were studying the lasso estimator, right? And there is this additional term, and this additional term, hopefully, goes to 0, right? So if we look at this additional term, what do we have? We have capital lambda times beta t minus beta star, right? So this is related to the error at step t, and what we hope is that the error at step t plus 1 will be smaller. So we hope that here we will have a contraction of the error. So of course it will not be always the case, it will depend on the matrix capital lambda, but under some condition on the matrix capital lambda, we will see that there is a contraction of this term, so it will decrease, and it will not go to 0, but just for simplicity assume that it goes to 0. Then if it goes to 0, essentially what you will have is beta star plus a statistical noise, and what you will do is apply hard-thresholding on this. So the idea is really that if we choose the right tuning of lambda, then this quantity here will be sparse enough so that lambda will act as a contraction. So really a contraction of the error. And okay, it will not go to 0, but let's say that it goes to 0. Then for t large, what you have that beta at t, when t goes to infinity, behaves more or less like the hard-thresholding operator applied to beta star plus z, where z is this noise term here. And this would correspond to the optimal optimization of beta star from the observation beta star plus z. So you see that this makes sense. So this is a discussion in order to discuss the difference with respect to what we have done so far, where we were really minimizing some criterion and starting from this minimization problem in order to analyze the race bound. Here, this is really a sequential analysis where we try to prove that zero error decreases toward some limit which corresponds to the minimax rate. So this is what we will see in a minute, but I think that because this proof is maybe a little longer than the other proof, we'll first do a coffee break. So what we want to do is to analyze the risk of this iterative hard-thresholding estimator. So what we will see, we see that under some conditions, so some condition on the parameter lambda t, so it will be condition on small a, capital A and B, and also on some condition on lambda, what we will see is that this estimator estimates beta star at the minimax grade. All right, so as for the lasso estimator, we'll first state a deterministic bound, and then, so this bound will have some condition, like this one, related to the noise level, and then we'll give a probabilistic version of this bound. So this is the main result here, and there are two important assumptions for this result. The first assumption is on the matrix capital lambda, which is, I remind you, identity minus x transpose x. And this assumption is similar to the compatibility constant assumption. It says that if you take a subset of a variable, they are not that far from being orthogonal. So more precisely, if you look at this matrix and you take any submatrix where you only keep some indices S of cardinality smaller than k bar, where k bar is 3 times the number of non-zero elements in beta star, then the operator norm of this submatrix must be smaller than delta, where delta is smaller than 1/3, right? So the star is not that large. So it means that if you look at the variable which are indexed by S, if you look at this matrix, it is not very different from the identity, and the difference in operator norm is smaller than delta. The second hypothesis, so this is really an hypothesis about the design, which is an hypothesis that we have already made, which is linked to a restricted isometry property. The second assumption is on the parameter, the choice of the parameter. So first, A must be smaller than 1/3 delta. Okay. and it must be larger than 1. A must be large enough, so I remind you that the value A, so maybe it is good to look again at lambda t, so lambda 0 is A plus B, so A is really what will drive the value for t equal to 0, so the initial value, while B is really what will drive the value of lambda t when t goes to infinity. So A must be large enough, and it must be larger than this quantity, which is in terms of beta star. And capital B, which corresponds to the limiting value, must be larger than this quantity, so you have this factor in terms of A. And here you have the infinity norm of x transpose epsilon, and this exactly corresponds to the noise levels that we have met for the lasso. So now, these are the assumptions that state the result. So we write m star for the support of beta star, right? So m star are the active variable in the regression. This corresponds to the value for which star j are non-zero. So we also look at m bar star, which is the complementary of the support. So these are the variables which are not active. And the first statement is that so this will hold for all t, right? So this statement holds for any value of t. So from t going to 0 to infinity, we will have that, so at any step t, the number of coordinates in beta at t which are non-zero and which are not in the support of beta star. So this is what is counted by this value. So I repeat, this is all the coordinates which are not in the support of beta star, but which are in the support of beta at t. So this number of variable is smaller than the number of non-zero coordinates of beta star. So maybe this estimator will select some variable which are not in the support of beta star, but not too many of them. Not more than the number of non-zero coordinates in beta star. And the second point is that when we look at beta at t minus beta star, this will be smaller than 3 times lambda t times square root of the number of non-zero coordinates in beta star. And again, this holds for any value of t. Right? So when t goes to 0, this decreases to b. So at the end, we have something which is, when t goes to infinity, like 3b times square root of the number of non-zero coordinates. So before proving this result, let us discuss this theorem. So if you compare to the lecture notes, you will see that in the lecture notes there is an additional parameter which is c. So for simplicity here I have fixed c equal to 1. So if you look at theorem 6.1 in the lecture notes, you will see an additional c which gives more flexibility to the result. But for simplicity I think that it's easier to fix c equal to 1. First, let me discuss this result. So what we know is that this quantity, so we have already met this quantity when we have been looking at the lasso estimator. We know that it behaves essentially as a sigma times square root 2 log p, okay, up to some constant. So if you choose b equal to constant times sigma square root 2 log p, since lambda t will decrease to this quantity, for t large enough, the norm here, so the norm of beta at t minus beta star square, will be smaller than constant times the number of non-zero coefficients times log p, right? And this corresponds to the minimax rate, so we will have estimation of beta star at the minimax rate, under some conditions. under the condition that lambda fulfills this property, which is quite a strong property. So we will discuss this result in the next corollary after the proof of theorem. So this condition here, I remind you that what is the way we want to perform the analysis is by using this decomposition, where we say that at step t+1, we are hard-thresholding this quantity, which is our target, plus this term, plus the statistical noise, which we know is. So, and we want to have a contraction of this term, in order to have a contraction of beta at t+1 and beta star, right? And the hypothesis here on lambda, we ensure that if this is sparse enough, we will have a contraction of this term, and the contraction rate will be delta, right? So this is something that we will see in the proof. And so in order to have this contraction, we need beta at t minus beta star to be sparse enough, right? So beta star is sparse, so we need to have beta hat t sparse. And this is exactly the statement. This statement here tells you that beta hat t remains sparse. If you look at the sparsity at beta hat t, since beta hat t outside of the support, we have at most this number of non-zero coefficient, then beta hat t has no more than twice this number of non-zero coefficient, right? So when you will take the difference between the two, you will not have no more than twice this number of non-zero coefficient. So a last comment before proving this theorem about the condition 6.10. So this condition here on the design, well, you can check that actually it ensures it's even equivalent to this property, which is the restricted isometry property, which tells you that when beta has a number of non-zero coefficients smaller than k bar, so remind you that k bar is 3 times the number of non-zero coefficients of beta star, then the square norm of x beta is similar than the square norm of beta square, and the ratio between the two is somewhere between 1 plus delta and 1 minus delta. And I think that you should check it, so take your pen and check that this holds. In particular, we see here that this is quite a strong condition, since it means that when beta is sparse enough is here, x essentially behaves like an isometry, so it means that we have some local orthogonality of the column of x. Local is with respect to the number of columns that we are looking at. Right, so let's prove this theorem, and what we will do, so we will assume that this holds at step t, and we will prove that it holds at steps t+1. And of course, we have chosen the initialization so that this holds for t equal to 0. If you look at t equal to 0, because of the choice of A, you will have this property and this property. So sorry, for beta hat 0, you have this property, of course, because you have 0 here, so this holds. And if you look at this property, it holds thanks to the choice of A. So this result hold for t equal to 0, and now we assume that it holds at step t, and we prove that it holds at step t+1. Let's do it. So we introduce a couple of notation for this. So I will call, like for the analysis of the lasso, Z, which is X transpose epsilon. And I will introduce bt+1, which corresponds to the value after one gradient step and before the thresholding. So I remind you that if we look before the gradient step, so this is the gradient step. We have seen that it is equal to this quantity. So this is what we call bt plus 1. So that beta hat t plus 1 will be the hard-thresholding of bt plus 1. Okay, so this is bt plus 1, and we apply the hard-thresholding on bt plus 1. And also, in the following, I will use k star for the number of non-zero coefficient of beta star. So, as I told you, we assume that the properties I and 2I holds at step t, and we want to prove that it will hold at step t plus 1. And the key point for this will be this contraction property, which says that if property holds at step t, then if you take any subset S of 1p with cardinality smaller than k star, so k star, remind you, is a number of non-zero coefficient of beta star, then you have this contraction. So if you look at bt plus 1 minus beta star, that you restrict to this cardinality S, the norm of this will be smaller than delta times the norm of beta star minus beta hat t, plus this term, which corresponds to the statistical noise, which is square root of the cardinality of S times the subnorm of Z. So this is really a contraction, because so this is what appears here when we do a gradient step. And what we see is that when we do a gradient step, at least if we restrict to a subset variable, then we have a contraction. This will be smaller than what we had at the previous step by a factor delta plus some noise term. So if this is very large, after some iteration, this will shrink to 0, and we will only have this statistical term that will remain. So this will be the key property for proving the theorem, which really gives you the contraction. So let's prove this line. So the proof is very simple, actually. You just have to check it. So essentially, you need some notation. So what I will do, I will code S tilde t, which is equal to the support of beta star union the support of beta hat t, right? So you can write it as the support of beta star, so which is m star, and union the support of beta hat t outside of m star, right? So this is equivalent, and I write it like this in order to see that this the cardinality of this quantity, this has a cardinality smaller than k star, and this will also have a cardinality smaller than k star, simply because the property here holds at step t. So this, the support of this vector has a cardinality which is smaller than k star, which is this vector. And I will also introduce S prime, which is S union this support of beta hat t union the support of beta star. So if we look at the cardinality of S prime, so it is smaller than the cardinality of S t plus the cardinality of S. We have already discussed that this is smaller than 2k star, and by assumption here you have that this is smaller than k star. So the sum of the two is smaller than 3k star, which is our bar k appearing in condition 6.10, right? So we'll be able to apply condition 6.10 to S equal to S prime, this S prime, right? So let us look at the quantity appearing in the lemma 6.2. If we look at this quantity, by the very definition of bt plus 1, which is given here, what we have is that bt plus 1 minus beta star is equal to this term, plus this term, right? So we will use the triangular inequality in order to get that this norm is smaller to the norm of this vector respective to S plus the norm of this vector respective to S, right? So we have these two terms. Now, let us look at these two norms. So first, for this term, we use the fact that S is a subset of S prime. So if you look at the norm of a larger vector, it takes more coordinates, the norm will be larger, so we'll upper bound by this norm. And here we simply use Cauchy-Schwarz, not Cauchy-Schwarz, we simply use the fact that each entry is smaller than the subnorm of Z, so this norm is smaller than the square root of the cardinality of S times the subnorm of E. So we will not touch anymore to this term, so this term will stay unchanged in the remaining of the proof of lemma 6.2, and we will only focus on this term. So if we focus on this term, we see here that we have a product of lambda with a vector, but the support of this vector is included in S prime. Actually, the support of this vector is included in S tilde t, right? So we can restrict here this vector to S prime, because S prime contains S tilde t, it contains the support of this vector. So we can restrict this vector to S prime, and we can restrict at the same time the matrix lambda by only keeping the columns of lambda which are in S prime, right? So we can restrict the vector to S prime and only keep the column of lambda which are in S prime. In addition, we are looking at the entries which are in S prime. So if you look at the entries which are in S prime, it means that you are only looking at the entries which correspond to the row in S prime of lambda, right? So this quantity is exactly equal to this quantity. This should be equal, right? I have not changed anything, because here I have, so for this S prime, this is just due to the fact that we are only looking at the entries in S prime, and for these two S prime here, this is only due to the fact that the support of this vector is included in S tilde t, which is included in S prime. Right, so why did I write this term in this way? Simply because I want to use the restricted isometric property, so 6.10, this property here, and I will be able to use it because I have S prime, which has a cardinality smaller than k bar. So I use this property, and I got this contraction, this smaller than delta times this quantity. Okay, so this is just by hypothesis. It's a restricted isometric property. And now you have the same argument as here. We use the fact that if you look at the norm, well, actually, we don't not even have to use the same argument. We just have to check that since the support of this is included in S prime, the norm of the vector restricted to S prime is the same as the norm of this vector, since outside of S prime, all the coefficients are 0. So this is why there is an equality. Okay, so if you look, you have proved that this is smaller than this, and this is exactly the statement of lemma 6.2. So we have proved this contraction property of the gradient state. Okay, so this is here for the gradient update, and now we have to look at the iteration when we apply, in addition, the Hard-Thresholding. Right, so we'll use repeatedly this lemma, and for analyzing this quantity minus beta star, so once we have applied some Hard-Thresholding. So in order to analyze this difference, we will split the analysis in two parts, one part on M star and one part outside of M star. So let's just have a look first on M star. So if you look on M star, so we look at the difference of the two vectors, but only for the coordinates in the support of beta star. So first we will use the triangular inequality. So what we will do, we will add and subtract the gradient update beta t plus 1, and of course restricted to M star. So if you use this with triangular inequality, you got this inequality here, and now we will bound these two terms. So let us first look at this term here. So here we have the gradient update restricted to M star minus the hard-thresholding of the gradient update. Let me remind you what is hard-thresholding. In hard-thresholding, what you do is you only keep the value which are in absolute value larger than lambda, right? And if they are larger than lambda, you do not change them. Otherwise, you set it to 0. So if you look at the difference of alpha with the hard-thresholding estimator, what you see is that the difference will be equal to 0 if alpha 1 is larger than lambda, and the difference will be equal to alpha 1 if alpha 1 is larger than, is smaller than lambda. Okay, so it will be always smaller than lambda in absolute value, since it is non-zero only when alpha 1 is smaller than lambda. So if we come back to our difference here, what we have is that the difference, so each coordinate here has a value which in absolute value is smaller than lambda t plus 1, is exactly what we have discussed. And how many coordinates do we have? We have at most the cardinality of M star coordinate. So this term is smaller than lambda t plus 1 times the square root of the cardinality of M star. I think if it is not clear for you, you should take a pen and check it by yourself. It is quite easy, you just have to write it down. So we already have a bound in terms of square root of k star lambda t plus 1 for this term. So we have to look now at this additional term. If you look at this additional term, well, you will use the fact that M star has a cardinality which is equal to k star. So you're really looking at something of this form, right? With S equal to M star, which has a cardinality equal to k star. So you will use this inequality for S equal to M star. So if you plug in this inequality, you get this bound, right? And in this bound, you can now use the induction hypothesis. So you will use property 2i at step t. So 2i at step t, it tells you that the error is smaller than 3 lambda square root of k star, which is the number of non-zero coefficients in beta star. So this is what we get here. And at the end, if you add this term with this term and this term, since cardinality of M star is equal to k star by definition, you have square root of k star times lambda t plus 1. Here you have 3 times lambda t, and here you have the subnorm of z. And now we will use the hypothesis on the coefficient. So first, there is the hypothesis on small a. Remind you that small a is smaller than 3 over delta, right? And we will use the hypothesis on capital B, which is larger than a over a minus 1 times z, the infinity norm of z. So here I use the fact that A is smaller than 1 over 3 delta, so this is smaller than 1 over A lambda t. And here I use that the subnorm of z is smaller than A minus 1 over A times B. Now, what is this quantity? It is exactly lambda t plus 1. Why just use the fact that lambda t is defined by this equality. So it fulfills some recursion, which is lambda t plus 1, which is equal to 1 over A times lambda t plus B times A minus 1 over A. Right? So you have this recursion of order 1. So at the end, we have twice lambda t plus 1, so we have this bound, which is 6.17 in the lecture notes. So what we have proved that if you look at this quantity at step t plus 1, if we restrict to the support of beta star, it is smaller than twice lambda t times this square root of k star. Right? So now we have to consider this vector outside of the support. And for this, the first step will be to show that there are not too many variables outside of the support which are selected. So we need to prove first this result here at step t plus 1. So for this, what we do, we take any subset S which is inside the support of beta t plus 1, but outside of m star. So it is inside the support of this vector. We take any S like this, which has a cardinality smaller than k star, which is the number of non-zero coefficients of beta star. Let us look at beta t plus 1 on S. So since S is in the support, first we know that all the values are non-zero, but even more, we know that since this has been obtained by some Hard-Thresholding, right? We have applied some Hard-Thresholding here. We know that since the values are non-zero, they are larger than lambda t plus 1. So we have cardinality of S value larger than lambda t plus 1. So the norm is larger than lambda t plus 1 times square root of the cardinality of S. Right? So we first have this lower bound. Now, again, we use the fact that S is in the support of beta t plus 1. So since it is in the support, it means that it has not been set to 0 by the Hard-Thresholding. So if it has not been set to 0 in the Hard-Thresholding, it means that they have not been changed when applying the Hard-Thresholding. So the entries of beta t plus 1 on S are the same as the entries of bt plus 1 on S, right? Again, this is obtained by applying Hard-Thresholding on this quantity, and since we are on the support, there is no value which are set to 0, so they are unchanged. Finally, we use the fact that S is outside the support of m star, so we can write this as the difference of this vector minus beta star S, since this is equal to 0. Okay, so I recognize again something as in lemma 6.2 with the cardinality which is smaller than k star. So I recognize really this situation. So I can apply this bound here. So if I apply the lemma, I obtain this bound. Okay, so this is a contraction. And I will also apply, again, as before, the result obtained in at step t on this norm, right? So this is my induction property, which tells me that this is smaller than 3 lambda t square root k star. So this is really this quantity. So and I'm lost, yeah, back, right? So we have this bound on this term. So again, I have something with square root of k star, because I know that this is smaller than k star, so I can have square root of k star in factor. And we know that the subnorm of z is strictly smaller than a minus 1 over a times b. And here again, I have 3 delta lambda t, which is smaller than 1 over a lambda t. And because of this recursion formula, here I recognize lambda t plus 1. So I have that square root of k star lambda t plus 1 is strictly larger than square root of the cardinality of s times lambda t plus 1. Since lambda t plus 1 is non-zero, I can cancel out the 2 lambda t plus 1, and I obtain that square root of the cardinality of s is strictly smaller than square root of k star. So what we have proved is that the cardinality of s is smaller than k star. Right? So what have we shown? We have shown that for any s which is in the support of beta at t plus 1 but outside of the support of beta star, which has a cardinality smaller than k star, then it must have the cardinality which is strictly smaller than k star. It means that we cannot find a set S in the support of beta at t plus 1 outside the support of beta star, which has a cardinality equal to k star. So in particular, the support here must have a cardinality which is strictly smaller than k star. Right? So this is what I have written here. We cannot find an S in the support of this vector with cardinality equal to k star. So it means that the cardinality of this support is smaller than k star. So this is this statement, and this gives us the property I at step t plus 1. Since the property I is that this is smaller than k star, here we prove that it is strictly smaller than k star. So we have proved that beta at t plus 1 is sparse enough. Outside of the support of beta star, there are at most k star non-zero elements, right? Which is the first statement of the theorem. So we have shown the induction for this statement, and now we have to prove the induction for the second statement. So if we look at the difference here of beta at t plus 1 and beta star outside of the support of beta star, so it is equal, so first it is equal to beta at t plus 1 outside the support of beta star, since this is equal to 0. And here we have this inequality. So if I take S equal to the support of this vector, which has a cardinality smaller than k star, this is what we have seen before, then if I apply this smaller to this inequality here, I obtain that the quantity that I'm looking at is smaller than lambda t plus 1 times square root of k star, which is this bound. So here we have proved that outside of the support, the difference is smaller than lambda t plus 1 times k star. So now I want to conclude. So in the support of beta star, we have shown that the difference between beta at t+1 and beta star is smaller than twice lambda square root k star. Outside of the support is smaller than lambda square root k star. So with a simple triangular inequality, we obtain that beta at t+1 and beta star is smaller than 3 lambda t+1 square root of k star. And so we have proved the second part of the theorem for steps t+1. Right, so we have proved that for a suitable choice of A and B, under this restricted isometry condition, we have these two quantities which hold for at any step t, right? So at any step, beta t is sparse, and in addition, it fulfills this condition. So for t small, lambda t is large, so it is not very interesting, but when t is going to infinity, t will be of this order of magnitude, and it will give us a nice statement. So before moving to the statement, to the probabilistic statement, which will be the next corollary, I think that we should have a break before stating the result. So what have we seen before the break? Before the break, we have obtained a deterministic bound, which under some assumption, which as here, gives some result on the sparsity of the estimator and the reconstruction error. So there are two questions now that we need to answer. So first, in this assumption, there is the choice of capital A and capital B, which are important since this corresponds to the choice of lambda. So we need to choose capital A and capital B, satisfying these two conditions. And these two conditions rely on some quantities that we don't observe, which are the norm of beta star, so we don't know the norm of beta star, and also the subnorm of X transpose epsilon, so the norm of the noise. So we need to find some capital A and capital B that we can compute from the data, so some data-driven value for capital A and capital B. And also, we need to stop at some point the algorithm. Here, we have a result which holds for any t, and I remind you that lambda t is of this form. So lambda t is, sorry, here. So lambda t is of this form. So lambda t is decreasing towards b at a geometric rate, and we have a bound which is in terms of lambda t, which is this bound. So the bound becomes better and better, but maybe we can stop at some point and not lose too much compared to t equal to infinity, right? So we have to determine for which value of t we have a result which is interesting. So this is what we will discuss now, the choice of t and the choice of capital A and capital B. So let us first discuss the choice of t. So as I've told to you, so the reconstruction error is proportional. So we have an upper bound which is proportional to lambda t times the square root of the number of non-zero coefficients in beta star. Lambda t is decreasing, but the idea is that first it decreases very fast, so it starts from a plus b, which can be very large, but then it decreases very fast to b at a geometric rate, right? So the idea is that if you choose a value t hat such that this quantity is smaller than 2b, then you have a bound where so lambda t will be smaller than 2b, so you are almost as good as the choice t goes to infinity, but you lose a factor 2. So the idea is that you can stop quite early the algorithm by choosing t hat, which fulfills this inequality. So if you want to fulfill this inequality, you have to choose t hat in this way. So the smallest integer larger than the logarithm of capital A over capital B, and here the logarithm is in a base of small a. Right, so we will have, so if A and B fulfills the condition 6.11, then we will have this reconstruction error with this choice of lambda t. So now we will choose A and B in order to have the condition 6.11 which are fulfilled with large probability, and we get the following bond, which is the corollary of the previous theorem. So this is an error band for the iterative hard-thresholding algorithm. As always, we stay in the Gaussian setting. We assume that all the columns of X have norm 1, and we assume also that the restricted isometry property condition hold. Then we will choose a K which will be larger than 1, and A, so A must fulfill this condition, so we choose any A fulfilling this condition. And we will set capital A and capital B in this way. So for capital A, we need to have something which is larger than the norm of beta star. And for this, we will make this choice with the norm of X transpose Y plus some corrective term in order to be sure that it will be larger than the norm of beta star. For capital B, we will choose something which is very similar to the choice that we have made for the lasso estimator. So we'll choose a constant sigma square root 2k times log p, right? And for this choice, so what we will prove in the proof of this corollary is that with large probability, at least as large as this, we have that the reconstruction error is smaller than some constant times sigma 2 times the number of non-zero coefficients times log p. So here I look at the norm square, so this is why I don't have any square root anymore. And this is exactly the minimax rate that we recover here. And we can also look at the prediction error. So we can look at, so this will be my f hat, this is my f star. So we look at the square norm between f hat and f star, and you get the same bound. You just have an additional 1 plus delta, and this simply follows from this bound with the restricted isometry property. And again, we observe that this corresponds to the Nimax rate. So we'll prove this result. And so as I've said, this is a consequence of this. Why? Because we have that beta hat t and beta star sparse. They have a sparsity which is smaller than k star. So if we use the restricted isometry property, this form of the restricted isometry property, then we obtain that x beta hat minus beta star to the square is smaller than 1 plus delta, the norm of beta hat minus beta star. So this is exactly the statement 2i, which follows from the statement I, right? So we need to prove this bond. So to prove this bond, of course, we will use our theorem, right? So in our theorem, so we have this bond that we will use. And first, we just notice that the bond that we have follows from the plugging of the value of lambda t hat for the choice of t hat. So we look at it again. So all we have to do is to check that these conditions are fulfilled with high probability, right? So let's do it. So first, as I have said, so for this choice here of lambda t, we have that this value of b with this value of a and b, so we only need b because here we only have b in the bond, will give us this upper bound, right? So this is simply a statement with b equal to this, right? And this bound with b equal to this. So all we need is to prove that A and B fulfill the condition 6.11 with at least this probability. So let us look first at the statement for capital B. So first, for the statement of capital B, so we need to prove that capital B is larger than this quantity. So we cannot have both capital B, the definition of capital B, and the probability that we need to compute. But if you look, this is exactly the bound that we have already computed for the lasso estimator. So you just have to look at the analysis done in the lasso estimator, so in the last lecture, lecture 4, in order to get this lower bound on the probability of having this inequality, right? So for this part of the condition 6.11, we already know that it holds with at least this probability. So all it remains is to prove the condition relative to capital A. So all we need is to prove that capital A is larger than this quantity. And actually what we will show is that capital A is larger than the norm of beta star divided by 3. Okay, we will not have some refinement in order to get refinement with this value. We just prove that it is larger than the norm of beta star by 3, which is enough. All right, so this is what we will prove. So with at least this probability, and actually we will prove that it is true with probability 1 minus 1 over p to the k, which is larger than this probability. So for this, we need to have a lower bound on A, and if we look at this quantity, this is non-random. The only thing which is random is this quantity that we use in order to estimate the norm of beta star. So in order to get a lower bound, a probabilistic lower bound on this quantity, what we need to use is, as usual, concentration inequalities, and in particular, Gaussian concentration inequalities. If we look at x transpose y, so y is x beta star plus epsilon, so it is equal to this quantity, right? And this map, it is Lipschitz with a Lipschitz coefficient, which is the operator norm of x. So we can use Gaussian concentration inequalities in order to get stochastic control of the norm of x transpose y. So we know that there are two exponential random variables which parameter 1, such that this lower bound and upper bound are right. So we want to have a lower bound on the norm of x transpose y. So actually we mainly use this lower bound here. But exactly as we have done in the first lecture, we want to have also a lower bound on this quantity, and this is not a quantity that we can handle very easily. We can handle much more easily the expectation of the square norm. So exactly as in the first lecture, we will also use this upper bound in order to get a lower bound on this quantity. So let's do it. So we start from this inequality here, then we put it to the square, right? And we take the expectation. So if we do this, expectation of the square, expectation of the square. And now, exactly as in the first lecture, what we do is to apply Jensen inequality, because the mapping which take xi prime and associate this value is something which is concave. So if you apply Jensen inequality, you can move the expectation inside the square root, and since the expectation of xi prime is equal to 1, we end up with this upper bound for the square norm of x transpose y to the square. So this is exactly as we have done during the first lecture. This gives us a lower bound on the expectation of the norm of x transpose y in terms of the expectation of the norm to the square, right? So now, if we look at this quantity, so the xi is this one, so I move this part on the other side. So I have the norm plus sigma operator norm square root of 2 psi. And I add also this term here, which is square root 2 sigma, the operator norm of x. Then I know that it is larger than the operator norm. So this is this inequality here. Sorry, not the operator, the expectation of the norm, sorry. So this is this inequality here, plus this additional term that I have added, right? Now, this term, I use this inequality, so I can bound it with the square root of the expectation with the square norm. And this expectation, you know how to compute it, right? You will have the square norm of the expectation, which is this quantity, since x transpose y is x transpose x beta star plus x transpose epsilon. So the expectation of x transpose y is x transpose x beta star. And you have the variance term. And the variance term, which is something which is non-negative, we will forget it. Simply, we will lower bound this quantity by the norm of x transpose x beta star. So now, so we have the norm squared of a vector, and we will again lower bound it by looking at the norm of a subpart of this vector. We'll only keep the indices which are in the support m star of beta star. Right? So I remind you that m star is equal to the support of beta star. Now, what we will do is to use that capital lambda is equal to 1 minus x transpose x, right? So here I can write it as identity minus lambda. This is in the right direction, so identity minus capital lambda. And then using triangular inequality, I have this lower bound here. And for this lower bound, so I will not touch this one, but for this one, what I can do, so first I look at the entries which are in m star, so it means that I only consider the row of capital lambda which are in m star, right? And then, so I have the product of lambda and beta star, but I remind you that beta star has a support which is m star, so I only have to take the product between the columns of lambda which are in m star and the indices of beta star which are in m star, because all the other products are equal to 0, right? So this quantity is equal to this quantity, right? It is not clear, you should check it with your pen. So now, why did I write it in this way? Because now I have some things that I can recognize. I have a submatrix of capital lambda, and I know that I have the restricted isometry property. So I know that this quantity is smaller than delta times the norm of beta star m star. So I have this lower bound here from the restricted isometry property. And to conclude, we use the fact that m star is the support of beta star, so the norm of beta star reported to its support is equal to the norm of beta star, so we have again this inequality. So now what we have proved is that this quantity divided by 3 factor of 1 minus delta is larger than beta star, right? So now if I look at A, what I will do is to replace xi by k log p, right? So if I replace xi by k log p here, in this bound, it will hold, so it will hold with k times log p if xi is smaller than k times log p, and the probability that xi is smaller than k times log p is at least 1 minus 1 over p to the k, right? So at the end, we obtain this lower bound with probability 1 minus 1 over p to the k, which is larger than this. So we have proved this bound. And to conclude, so we have proved that the two conditions hold with this probability. So the probability of the linion will hold with probability at least 1 minus 2 to the p 2 over p to the k minus 1. All right, so at the end, what we obtain is that under some condition which is quite strong, which is the restricted isometry property, for some suitable choice of A and B that are graph-driven, we have this bound, and we obtain a minimax optimal bound for the estimation with the iterative hard-thresholding algorithm. So to sum up, we have obtained some results which are similar as the result for the lasso. We have some conditions which are slightly stronger, but they are quite similar. Essentially, it means that we need to have some local orthogonality of the column of X. And this result, what a nice feature is that it is obtained for a number of iterations, t hat, which is controlled, which is the logarithm of A over B. So we have a direct control of the number of iterations that you need in order to get this result. So this is all what we see for the coordinate sparse setting. And now we'll move to more general settings. So as always, in order to understand what we can do in other setting, I will focus at the group sparse setting, which is the other case that we have been looking at in this lecture. And for the group sparse setting, we will do a very similar analysis. And we will see an algorithm, which is the iterative group thresholding algorithm. And for this, we will directly look in the lecture notes. So let's move on the lecture notes. So I'll remind you very briefly what is a group sparse regression. So we look at the regression model as usual. I will assume again that this aggregation distribution is covariance sigma 2 identity. And in the group sparse setting, what we have that our vector beta star, we know that there are some groups, so the groups are known. So there are some groups of variables like this. And this will be group 1, this will be group 2, so they may not be adjacent, but it's easier for the drawing to make them adjacent. So if I look here, I have beta star where I only keep the indices in G1, beta star in G2, in Gm, and in the group sparse regression, so we have group sparse if only a few groups or variables are non-zero. So only a few beta star gk is different from zero, right? So we want to generalize what we have seen in the iterative hard-thresholding to this setting, and we will look at it on the lecture note directly. So we are now on the lecture notes. So this is not the same number as you, as I have changed the display for the video. If you want to have the page, essentially you divide by 2, so it is 122, 123, and you will find this section, which is on iterative group thresholding, which is iterative hard-thresholding, but for a group regression. So I have said before, so my indices 1p are split into M group, G1, Gm, and we want to recover the groups Gj such that the entry is non-zero for this group, right? So if we look at the minimization problem, so for the model selection, what we did, we were penalizing by the number of non-zero groups. So if you forget about this lambda square here, you just take the sum of the indicator, you have the number of non-zero group. And classically, so we add a lambda in front of it, and you penalize by the number of non-zero groups. Here, we will use a slightly different setting, so we just generalize a little bit by taking some values that can depend. So the lambda will depend on the group. And essentially, as we see, a clever choice of lambda should depend on the square root of the cardinality of the group. So that's why we allow to have some lambda which depend on the cardinality of the group, right? So we look at this minimization problem, and this is the minimization problem that we would like to solve. This is our ideal problem, and that we are not able to solve, again, for the same reason as before, which is that here I have something which is non-continuous, non-convex, and so we are not able to solve it efficiently. So we want to use the proximal method. So we replace the quadratic term, the fit, by this linear approximation with a quadratic term which is simpler. And if we do this, so which is what we do for the proximal method, so we are at the current estimate beta t, and at the next step, so we solve this where we have replaced f by this approximation plus the penalization, and with exactly the same rearrangement as in the other case, the minimizer will be the same as for this minimization problem, where here I have beta minus a gradient update of beta t, right, at beta t. So this very much looks like what we had in the coordinate sparse-fitting. If you come back to the coordinate sparse-fitting, somewhere above. So if you look in the coordinate sparse-fitting, sorry, yes, we are minimizing this quantity. So we had beta minus gradient step, and here what we had was lambda 2 some indicator beta j different than 0, right? So here we have the same quantity, except that instead of having beta j different from 0, we have beta group j, gj different from 0, right? And it turns out that, again, we have an explicit solution for this minimization problem. And what is the explicit solution? It is what I will call the group thresholding estimator, where for each group, we will set the value to 0 if the norm is smaller than lambda j, and otherwise we let it unchanged, right? So what we will do, okay, I will move on to the blackboard. So if you look at your different entries, what you will do is, if this entry is larger than lambda 1, you will not change it. And if it is smaller, the norm of this entry is smaller than lambda 1, you will set it to 0. So this is exactly the same as for R thresholding, except that you are not thresholding each entries, but each groups by looking at the norm of your vector in this group. So we obtain that the R thresholding, the group thresholding operator here, will give me the solution to this minimization problem. So again, I apply it to the gradient step here. So I have made my gradient step, my gradient update, and I will apply the R thresholding at level, which is, so if I define lambda square root 2 eta, so here it means that I will not choose lambda j, but lambda j times the square root of 2 eta, right? So we have the same kind of iterative algorithm, except that instead of applying R thresholding, we apply group thresholding. And for the same reason as before, as this minimization problem is not convex, we have no idea of what these iterations are doing. We do not know if they converge to anything. And in particular, in general, it will not converge to the solution of this minimization problem. So we'll do the same thing as before. We will choose eta equal to 1/2, so that here we will have 1. Okay, so we take gradient step with eta equal to 1/2, and we will choose, we start from 0, and we choose a sequence lambda, so all the lambda j will be lambda j of t, with lambda j of t goes from a large value to the target value, which corresponds to minimax optimal estimation. Right. So this is what we will call iterative group thresholding. So we start from 0, we iterate these updates, right? So this is gradient update and group thresholding for some level that will decrease with t exactly the same way as before. So you can rewrite the update in this form if you prefer. For each group, what you will do is take a gradient step and then apply a group thresholding. So as I told you, we will choose some lambda, which will depend on the size of the group. And what we will do is to take the square root of the cardinality of dj times the quantity lambda gamma t, that will decrease, and that will be exactly of the same form as for hard thresholding. So we take gamma t as a minus t times capital A plus capital B. Right? So this is the settings that we will consider, and for which we will be able to prove some result. Actually, you will be able to prove some result. So we need a couple of notations that will be the counterpart of the quantity that we have introduced for iterative hard thresholding. So first, what we call the group support of beta is the union of all the group for which we have non-zero beta, right? So it can be somewhat larger than the support of beta if there are some zero value. So if some group, beta dj is non-zero, but there are some zero value, some zero coordinate. So in this case, it will not be equal. If when a group is non-zero, all the coordinates are non-zero, then this will correspond to the support of beta. So we will denote by beta 0j the cardinality of this group support, right? And we introduce this norm for z, which is the maximum of the norm of z restricted to the group j divided by the cardinality of j with the square root, right? So if you take for each group just a singleton, so if you say that you have p group with just one element, of course here you recover the support, and here you recover the subnorm, right? And here you recover exactly the same number. So with this notation, now we can analyze this iterative group thresholding algorithm, and we can look at the deterministic bound, which is, as you can see, really similar to the bound that we have for the iterative hard thresholding. So if you look at this bound, you see that you will have some assumption. So here there is an assumption. So for simplicity, we assume that all the groups have the same cardinality, which is equal to Q. So this will simplify the analysis. And we have this condition, which is exactly the same condition as 6.10, but in our setting. So we look at some support which are union of groups, right? With not too many groups. So this is the condition that we are not looking at too many groups. We have this condition of A that we have already met. So it was with C equal to 1, but if you take C equal to 1, you have 1 over 3 delta. We have these two conditions. So A must be larger than this quantity. So this is exactly the same as for iterative hard-thresholding, except that we are looking at the J0 pseudonorm. and you have this condition of B, which is also the same as for the iterative hard-thresholding, so the condition 6.11, except that here we are looking at this norm instead of the subnorm, right? This norm being this one. So what are the statements? The statement is that, so if A and B fulfill these two conditions, or if we have this restricted isometry condition, then not too many groups are selected. So if you look outside of the group support of beta star, we have that no more than this number of groups are selected, right? So we do not select too many groups outside of the support, the group support of beta star. So this is really the same statement as before, but for groups. And we have this bound, so this holds for NET, which tells you that the reconstruction error is smaller than constant time gamma t times square root of the number of non-zero coefficient in beta star 0. So as you can see, this is very similar to what we had for iterative hard-thresholding, and the proof is also very similar. So a good way for you to get familiar with this analysis and to get familiar with the analysis in iterative hard-thresholding is to prove this result, which is the exercise 643, and the exercise 643 is one of the assigned exercise for this lecture. So this is the assigned exercise for this lecture. So you will prove this bound by following the same reasoning as for iterative hard-thresholding. Right, so now that we have this result, that you have proved that these results hold, then as before, we need to choose A and B in order to have this condition with high probability, right? So for A, since our choice of A guarantees that A was larger than just beta star, we do not have to do anything, we just can use the same A. But for B, we have to choose B, so that B is larger than this. So now we have to handle this quantity instead of the subnorm of Z. So we choose a B adapted to this quantity. So same A, and for B, we will choose this. So if you compare to the B that we had, so the B that we had before was A sigma over A minus 1 square root of 2 log P, essentially. So square root of log P with some constant, so 2k log P. Here, what changed is that instead of having log P, we will have log M, right? And we have this phi j, which appear here, which is related to the operator norm of X. So this is the operator norm of xj over the square root of the cardinality of j, maximum over all the rule, right? So we have this factor here. So if we compare to the b that we have taken, so instead of having log p, we have log m. Now this is something smaller, but we have this constant which can be possibly larger than 1, right? And exactly as before, we choose t hat as being the smallest integer, larger than the logarithm of capital A divided by capital B in the basis small a. So if you use this A and B, we will have that with large probability, this will hold. So the statement will hold with this value of A and B. So we obtain the following corollary, which tells us that under the assumption on a restricted isometry property, for this choice of A, small a, and for this choice of capital A and capital B, we have this reconstruction error, which is that the difference is smaller than the number of non-zero groups times sigma 2. So this is not the number of non-zero groups. This is the group, the size of the group support of beta star times sigma 2 times this term where we have logarithm of m times this constant phi j to the square, right? So essentially here we have replaced log p by this quantity, which is hopefully smaller. It will be actually smaller under the condition that we have imposed. All right, so again, you will also prove this corollary in the exercise. So what we have obtained is that we have very similar results simply by adapting the analysis and the algorithm to the group sparsity. Essentially, we have taken the initial minimization problem. We have used the proximal method to obtain this kind of iteration, and then we have adapted the level by choosing this lambda t in order to ensure sparsity, group sparsity of our solution, and together with this condition, which is a restricted isometric property for the group setting, we get that we have some nice result which are similar as for the group lasso for this algorithm for t equal to t hat, or t larger than t hat. Right, so I think it is time to have a sum up of this lecture. So I remind you that what we have seen at the very beginning of this lecture is that convex relaxation is near optimal, numerically tractable, but it suffers some bias. And what have we seen today? What we have seen is that if we replace convex relaxation by some iterative algorithm, then we still have near optimality. It is very efficient computationally, and we do not have this bias anymore, because instead of having some shrinkage from the soft thresholding or from the group soft thresholding, we have hard thresholding that does not shrink the solution. So we have some nice result both in theory and in practice. That's all for today. I wish you a very good week, and see you soon.